Hello. Is there anybody there?
Yes.
So good morning.
Good morning.
So today we'll talk about the carbon-13. Do you see the slide?
Yes.
Yes.
Okay. We'll see. Well, for the carbon-13, as I said, it will be the same phenomenon as the one we talk about for the proton. We observe carbon-13 because the I number is different to 0. And the carbon-13 behave like a small magnet, just like the proton. And in the magnetic field, they will interact with proton in the molecule. And we'll see that we will not be able to see the coupling between carbons, and we'll see why. And we'll see also that the scale, you can see here on the picture, the scale is broader than the one in proton. But what we observed, the way, the different way the frequency of resonance are, has the same reason that the one for the proton. It depends on the chemical groups in the structure. So we're going to see how to interpret this. So as I said, NMR, carbon-13 NMR is the same phenomenon, or is based on the same phenomenon as for proton NMR spectrum. We don't observe the carbon-12 because it doesn't have a spin number, so we don't have NMR phenomenon. But we can observe the isotope carbon-13, but the problem is that the natural abundance is very low, only 1.1%, compared to the proton, which is around 99%. So to observe carbon-13, we will need a biggest amount of compounds in the NMR tube, or a longer time of experiment to have a nice spectrum. As I said, because of this low natural abundance, it's rare to have two carbon-13 side by side in the molecule, so we won't be able to observe the coupling between carbon-13. So this is nice for us because we won't have to interpret the multiplicity. But we are able to see the influence of the proton on the carbon-13. So we can observe the coupling between both proton and carbon-13. And we'll see how to interpret this, but it's more simpler than for the proton. So again, we will be able to measure the coupling constant between carbon and proton. And the value of the coupling constant will depend on the distance that separate the carbon and the proton. So we will be able to measure J1, J2, J3, J4. And as far as the proton is, as lower became the influence or the coupling interaction with the carbon. So the J will decrease. For the carbon-13, I will not enter the detail, but we will not have the integration information. It's for the carbon-13, the surface under the peak is not proportional to the number of carbon having the same frequency of resonance. So no integration, no coupling carbon to carbon. So we have almost only the frequency of resonance or the chemical shift to based on to determine the structure. And as I said, the scale, as it's a carbon-13, the range of frequency of resonance will be different from that for the proton. Remember, the proton, we will have a scale from 0 to 12 ppm approximately. But in carbon-13, we go from 0 to 220 ppm. So the scale is broader. But what stay the same is the rules for the shielding and deshielding phenomenon. That means that the way the chemical groups are giving electro donor or electro withdrawer, it's the same. So if we increase the density of electron around the carbon, we will decrease the chemical shift. But if we decrease the electronic density around the carbon, we will increase the chemical shift. We will see that later. So every organic molecule has a carbon skeleton. So it's very important to be able to measure or to interpret the carbon-13 spectrum. It will give us many information on the detail, on the structure, on the chemical groups, and so on. So this is again to tell you why we have this. We need this. Well, we have the less sensitivity compared to the NMR proton. It's because of the low abundance of the carbon-13. It's, as I said, 1.1% compared to the carbon-12, which is almost 99%. So here we have the comparison between the way of the range or the average value of frequency of resonance for the proton. We use the B0 of 300 megahertz for the proton, but for the carbon-13, the range is different. We are around 75 to 125 megahertz for the value of B0. And the range of the chemical shift is from 0 to 220 ppm. So the carbon-13 looks like that. So we have the scale going from 0 to 220 ppm. And as you could see, the signal is not as nice as in proton because of the low abundance of the carbon. We have a baseline which is very thick and very black. And that's why we need a lot of, a great amount of compounds in the tube to have a better signal than the noise of the signal. So here for this molecule, for example, we can count 1, 2, 3, 4 carbons. So on the NMR spectrum, we should see 4 signals for each carbons. If we have no symmetry, then we will have the same as much as signal than as much as carbon in the structure. And you can see that they don't have the same chemical shift. And this is directly related to the nature of the chemical groups in the molecule. For example, methyl groups here, carbon 1 and carbon 4, as they are methyl group, they have a low chemical shift. It's between 10 and 20, depending on the chemical groups around. For example, carbon 1 is more deshielded. Let me take my... Yes, carbon 1 has a chemical shift that is higher than carbon 4. So we say that it is deshielded. It is the same as for the proton. And it is deshielded because on carbon 2, we have a carboxyl group, which is withdrawing chemical groups. So the electronic density is lower on the carbon 1 because of this chemical group. So that's why, compared to carbon 4 here, we have a deshielding effect on carbon 1. And the same for carbon 3, for example, as you see, the chemical shift is around 60 ppm. It's because it's directly linked to an oxygen. An oxygen is a very strong withdrawing group because oxygen is more electronegative than the carbon. So carbon 3 will be very deshielded compared to the carbon 1 and carbon 3. And finally, carbon 2, as it is the carbon of the ester group of the carbonyl, it's very, very deshielded. We are around 170 ppm. So we have the same rules between proton for proton and carbon to understand why the chemical shifts are different. So as you could see here, for each carbon, I have only a singlet. But we will see it's not really the case. This is because we have done something special to have only singlet for every carbon. Here is just as an example to have a different kind of nucleus and see the value of the spin number I. And you can see that for the proton, we have a spin number of 1/2, but it's the same for carbon 13, nitrogen, and many other elements. For example, phosphorus also, fluorine. And what will depend on what the signal will, the goodness of the signal will depend on the natural abundance, but not on the spin number, because the spin number is the same between them. But you can see that the most abundant is the hydrogen, and you have the carbon-13, and then the nitrogen. So that's why if you want to work on peptide or protein and you want to observe nitrogen, you need a higher amount of compounds in the tube than the carbon-13. And for other elements, you can see as soon as the spin number is different to 0, we should be able to observe the NMR phenomenon. Here is the table that it would be great if you could have some value in mind. For example, you can see, well, the scale is going like that. And it's the same way that we observe for the proton. That means that if you have an aliphatic molecule, the carbon will be between 0 to 50, 40, let's say. But you see, as soon as you add an oxygen, we go over 50 ppm. All the green one are carbons in aliphatic protons without any heteroatom just beside. But if you add, for example, we saw in the structure before, if here or here you have a carbon with a double bond, we goes over the 50 value. So from 50 to 80, something like that, we have carbon wearing oxygen, for example. And starting from 100 to 130, 130, 140, we have double bond, carbon to carbon double bond. And over 150, it's we will find carbon in wearing heteroatom like that, or in aromatic ring also, aromatic wearing oxygen and so on. And then some chemical group, special chemical group like ester, as we saw before, carboxylic acid, aldehyde group, ketones, we are over 170. Some ester group, sometimes it's 168, but it's over starting from this value. So for the exam, I will give you a table, but if you could have these kind of just to keep in mind that aliphatic carbon are there, carbon wearing oxygen are between 40 to 80, 90, double bond between 100 and 130, and then carbon wearing double bond and heteroatom are over 160. It could be great and easily for you doing the exercise. Okay, so as I said, you start to understand that we will have the same kind of effect. This is the same molecule we saw before, the same spectrum. And as you could see, we will have a change in chemical shift depending on the chemical groups in the structure. And as the same, we will use the same vocabulary. If the chemical shift increase, then you will have a de-shielding. And if it decrease, you will have a shielding effect. And so we explained before why we have these different chemical shifts. So it's the same. Again, here you have the average value of chemical shift for carbon-13 NMR, depending on the electronic density around the carbon. And of course, it depends on the chemical groups. This is quite the same as we have just done before. So it's another way to make a figure. Okay, so we will play with this example to understand the effect of the mesomeric effect on a double bond. It's exactly the same as we have in the proton. For example, if this is the reference value with the delta here, delta value is the same everywhere because the molecule is symmetric. If we goes here to the first example, we add in the structure an aldehyde group, but it could be also a ketone or an ester group. It will be exactly the same. We have a withdrawing effect of the oxygen because of the difference of electronegativity. And this withdrawing effect is conjugated to the double bond. So we will have a movement like that from the oxygen until the carbon at the end of the molecule. So the electrons that are here on the bond, the chemical bond, we will goes to the carbon, which means that here the electronic density will decrease. And so the chemical shift will increase. So here we will have, because of this mesomeric effect, we will have a chemical shift that will increase compared to the chemical shift at the beginning. And in the second example, second molecule, here we have a group that it's an ether that is conjugated to the double bond, even if the oxygen is more electronegative than the carbon. Here, because of the mesomeric effect, the mesomeric effect will be higher than the inductive effect. So the doublet of electron here will be withdrawn by the double bond, and we will have a movement of electron like that. So the electrons here will go to closer to the protons, so the electronic density will increase. That means that the chemical shift will decrease. We have a shielding effect. So here we have a delta minus because it's richer in electrons. Oh, sorry, it's here. Here we have an shielding effect. And here a de-shielding effect. It's okay for you?
Yes.
Okay, so we have the same phenomenon in aromatic derivatives. We start to see that yesterday. So when you have a donor effect, which is either an inductive or here a mesomeric effect because of the conjugation with the aromatic ring, then you will have a decrease effect of the chemical shift compared to the benzene. Instead, if in the opposite, if you have a withdrawing effect because of a mesomeric effect, for example, here, or but also if you have an inductive effect, then you will have an increase of the chemical shift on the carbon here, here, and here. Remember, so we can say here you have a strong delta plus effect in ortho position and a small delta plus in para, and you have a small delta minus in meta position. And here we have a strong delta minus in ortho, small delta minus in para, and small delta plus in meta position. And here, what is different is for carbon 1, here, the green one, because it is directly linked to the oxygen, here it's the difference of electronegativity that will play. And carbon 1 will be very de-shielded compared to a carbon wearing a proton. Remember the table. So this carbon will be around 150. And 145. But the other carbons here will be, the red one will be around, we just have seen that. Well, let's give a wide range. Let's say 125 to 100 delta for the carbon, the other carbons. Okay, so this could help you. Please try to understand this very well because it will help you to interpret the carbon 13 spectrum. Here you have a table again. They are different, but they say exactly the same. As you could see, it's the same. It may be more precise than the other table we used before, but it says exactly the same. Ether, amide, ester group are between 160 and 180. And ketone and aldehyde group are usually between 190 and 220. And the other aromatic carbons that were hydrogen, they are between 100 and 150, but as soon as you introduce heteroatom, then you goes over 150. and so on. So this is very important to understand. This is another table, but it's exactly the same, so I won't go through this. So now you have to understand that usually at the beginning, if we don't do anything, we don't ask the computer to change the way the spectrum is, we should see something like that. That means that each carbon should, if it is close to a proton, we should see a coupling between a proton and a carbon-13. And the rule, the splitting signals is the same, is M equal N, 2N plus 1. That means that as I here is also 1/2, M equal N plus 1. And N is the number of hydrogen on the carbon. That means J1. And sometimes you can see also J2, J3, but let's just talk about J1 coupling for now. So if you see on the spectrum a doublet, this is a doublet, then you should think that this is a CH group. If you have a triplet, that means that you have a CH2. If you have a quartet, this is a quartet, and you have another one here, another one here. So that means that you have CH3 group. And we don't see it here, but if you have a singlet, let's say here, that means that it's a carbon without any proton on it. That means it's a quaternary carbon, just like ketone, not at 160, but an ester group, for example. There is no proton on it. So it's a quaternary carbon. Okay. So keeping the spectrum like that could be easier to interpret if we have small molecule with a small number of carbon. But if you have, let's say, I don't know, 30 carbons or 27 carbon, you won't see anything in the structure. Okay, let's go further. So we need to do something to make the spectrum simplest if you have a great number of carbon. So just come back a little bit. This is just to show you that when we have a quaternary carbon, usually at the beginning we have a singlet, a CH2 a doublet, a CH3, a CH a doublet, a CH2 a triplet, and a CH4 a quartet. So the multiplicity, as you could see here in the figure, as you could see, going from the singlet to the quartet, you see that the signal decrease the higher of the signal decrease, because for each of them it's only one carbon, but the surface under the peak is distributed between each line. So here it's the surface goes from here to here. So even here you have a surface. And as soon as you hide the number of line, of course, you lower the high of the signal. So we used to say that the multiplicity will decrease the ratio between the signal and the noise, and also you decrease the sensitivity. So that why we will do something to suppress the multiplicity, and we'll have only singlet for all the carbons to have a greater sensitivity in the signal. So this is another example, for example, for this molecule, the ethyl bromide, and you see that the CH2 is here and the CH3 in blue. They are close together, but if the environment is not that different, they could be overlapped, and it will be very difficult to interpret. So that's why usually we make what we call a decoupled spectrum. That means that when we register the spectrum, we suppress the coupling with the proton, doing what we call an irradiation in the frequency of resonance of the proton, and then we suppress it, just like we suppress the signal or the influence of the proton on the carbon-13. Then we suppress the coupling, and then we have only singlet for all the proton. From a multiplet, we'll have only a singlet. What are the consequences? Consequences is that we have a greater sensitivity because we don't have the influence or effect of the protons and the coupling with the protons on the carbon. And then we increase the signal. From a small signal, we will have a greater signal. But this is true if the carbon are wearing hydrogen. We won't have this increase of signal for quaternary carbon, of course, because they are initially not coupled to any protons. So, for example, this is what we work with. Remember the structure. And then initially we can see the different type of signal. Doublet here, triplet, quartet, and quartet. This is the solvent. The TMS, the reference, the zero reference. But if we decouple, then you see we suppress the coupling between the proton and the carbon. So then we have only singlet for every signal. So it's easier to interpret. And what is more real, it's when the molecule is very complex, just like cholesterol, for example. If we keep the coupling between carbon and proton, you see here we have a doublet. And here we have also a doublet. Here I can imagine a triplet, but other signal, they are very difficult to interpret. I don't know what kind of peak I have to choose. So that's why it's better to decouple spectrum. And then we know that the coupling is suppressed. We have a decoupled spectrum. And then we have only singlet for every carbon. So here I see this is the doublet. Here it was the triplet. And I see that here and here I have two different carbons. They were starting one here and one under there. So now we can see them properly, and this was not the case in the coupled spectrum. And the same for all the other, except for that one that we knew initially that it was a doublet. So it's usually in life we prefer using decoupled spectrum. But there are some experiments that we use to, and we want to keep the coupling, but we have a way to print the spectrum so we can interpret it anyway. These experiments are called depth. And depending of the experiment, we have many different kind of experiment, and we will see what kind of result we have for each of them. In practice, we used to combine normal carbon-13 decoupled combine to the other experiment to have the most information that I can get. Especially, I want to know if I have quaternary carbon, CH, CH2, or CH3. And we will combine all the data from this experiment. So this experiment, as I said, is also used to enhance the intensity of the signals for the carbon-13. First, we suppress the coupling. So for one peak, I will have one carbon, but we will do also other experiments. For example, the depth 90 degree. And then if we have the scale here, the scale, this is let's say the medium line. We said we have a positive side and negative side. Just to say it's up and down. It's the only, say, up the scale and down the scale, or up and below, just the same. So on when we do the depth 90, the experiment, we will observe only CH2 carbon. It will suppress all the other. So I will see only signals for CH2, and they will be on the upper side of the spectrum of the baseline. If we do the depth 135, we will part the signal in two. On the upper side, we will have the CH and the CH3. And in the lower side, we will have the CH2. We observe no quaternary carbon. And there is another experiment which is called J for the coupling constant modulated. And then we have all the carbon, but quaternary carbon, CH2 are on the upper side and CH and CH3 on the lower side. So when we combine the spectrum, the decoupled spectrum with all singlet for every carbon, to these other experiments, we are able to identify which signal is a CH2, which one is a CH or a CH3 or a quaternary carbon without any coupling multiplicity. So it's greater signals, but also easier to interpret. So these are the different kind of experiments, and what we can have as information. So the decoupled carbon-13, we will see all the carbon. With the depth 45, we'll identify the only protonated carbon. On the carbon, the depth 90, we will identify the CH. And with the depth 135, we distinguish CH2 from CH and CH3. And we don't observe any quaternary carbon. So what does it look like? For example, this is a J-modulated spectrum for this molecule. If you have the structure, it's easy to identify the carbon. Depending, using a table, you will be able to identify the carbon. For example, the carbon 9, it's a CH2. The carbon 7 and 8 are CH because they are on the opposite side. Remember, the scale is going this way. Then we have the CH, but because, well, I didn't keep, where is my, I didn't keep the scale. Yeah, the scale should be there. And here we are around 150. All these are remember, from 100 to 130, for example. Here we are around 70. Here CH2 is around 60. CH2 wearing an oxygen. Okay, we have an oxygen. And here which is a methyl, but a methyl here on an oxygen also. On aromatic ring, we are around 53. This is the solvent. Okay, so with this kind of spectrum, it's easier for us to identify the type of carbon, if they are quaternary, CH and CH3. For example, here, the last one, you see the high is very smaller than the others. Then I knew that they should be quaternary carbon. And if I check the chemical shift also, they are here, carbon 3 and 4 for the most deshielded, and the less deshielded should be, the last one, the carbon 1. Okay. So usually we combine all these experiments in carbon-13 to have a great number of information. So for example, for this other molecule, we start here with the carbon-13 spectrum on decoupled, I repeat, decoupled spectrum. So for each carbon, I have one singlet, one signal. I know I can count. I know 1, 2, 3, 4, 5, 6 carbon in this structure. I can give them a name. And here we wrote the chemical shift. So they are named A, B, C, D, and so on. And these are the value of the chemical shift. But usually we compare it with the other depth experiment. So for example, the depth 145, depth 45, we will be able to see all the carbon except the quaternary carbon. So looking at this, I can say, well, where is the carbon C here? So it should be there. As I don't see it with the depth 45, then I knew that carbon C is a quaternary carbon. For the other, when I will use the depth 90, for example, and I observe only the CH in the structure. So then I knew that carbon E and D are CH carbon, because it's the only signal I have on this experiment. And if I compare with the depth 135, I can see the CH3 and CH on one side of the spectrum and CH2 on the other side. That's why we call positive and negative side. Then I knew that B is a CH2. Carbon B is a CH2. I saw the CH, so it's confirmed here. And the carbon F and A are CH3 carbon. Okay, so it's important to always compare with the original carbon, but the decoupled carbon. Again, here we could use the coupling or coupled spectrum because the structure is small. You don't have a great number of carbon. But if you have a great number of carbon, for example, like the codeine, you see it will be difficult if we have all the multiplicity. So again, we will be able, compared to the normal carbon-13, we will compare and identify the CH, the CH2 in the structure, and the CH3 also here, and all the other CH, and all the small signal are quaternary carbon. I don't observe them anywhere. Okay. So what time is it? So if you want, we can make a stop of 5 minutes and we come back to end this lecture and try to make the correction of the exercise. Okay?
Okay.
So see you in 5 minutes. So do you see the slide?
Yes.
To finish this lecture on carbon-13, I would like to tell you about the theoretical calculation of the carbon-13 chemical shift. Remember yesterday I told you that we can do that for aromatic protons, but we can do that also for carbon-13, and sometimes it helps to draw and put the substituent on the aromatic ring. So what we use, we start from the theoretical value for the carbon in the benzene, and then with the table, this is the table, the theoretical value for the carbon of an aromatic ring without any substituent is defined as 128.5 ppm. This has been calculated by some scientists. And then, depending on the chemical groups at the position here, 1, we will have some change of this theoretical or starting value. And then we should add all these effects depending on the number. If you have 2 or 3 substituents, you will add the effect or subtract the effect depending on the donor effect or the withdrawing effect of all the substituents. So we'll try to make an example. So if I will give you the table, of course, you don't have to learn this, but you can see that if you consider the carbon 1 here, if on carbon 1 you have a methyl group, you will have an increase, an increase of the chemical shift of the carbon. But if you have, this is a triple bond, for example, or an iodine on carbon 1, then you will have a decrease of the chemical shift because you will have to subtract 334 ppm from 128 and so on. So how to use it? For example, with this structure, we will do together the carbon 1, and then I will let you do for the 5 other carbon. So we are calculating the chemical shift for carbon 1 here. So we start with the theoretical value, which is 128.5. And then we will look what is on the carbon, but also what is on the carbon on the nucleus, on the ring, on the aromatic ring. So here on position 1, if I go back to the table, I see that on what is the OCH3, on carbon 1, I have OCH3. That means that there is a mistake in my slide. I should add 31.5. If I go there, this is wrong. I have to add 31.5. on the carbon side, on carbon 2, so that means this is Z1, this is Z2. If I go back to the table, in Z1, I should add 31.4, but in Z2, in this position, I have another group, which is a CH2 with a carboxyl. Sometimes we don't have exactly the right chemical groups. CH2, I don't know if we could see that somewhere else, but it's something like that. So that means that I should add 1.5 ppm because the sulfur here is has the same behavior than the carbon with the double bond. So approximately we can add 1.5 ppm here. So the chemical shift, the theoretical chemical shift will be calculated. 161.5 ppm. Do you want to try for carbon 2? Do you have the table in your document? I sent it to you yesterday.
Yes, can you give us a few minutes to calculate it?
Sure, sure.
Okay.
Are you ready? Hello?
Yes.
Yeah. Can you tell me what you have found for the carbon 2?
I got 132.1.
Can you just tell me what you have chosen? So you did you add or you subtract?
I add the COOH group. Suppose.
Well, if we let me change this. So now we are looking at carbon 2 here. This position is considered at Z1, and here is Z2, here is Z3, and so on. Okay? Here, Z2, Z3, and so on. So if I come back to the table, I want to have in position Z1, just like X, this group. And remember, we didn't find it exactly. So, but we found something quite, not exactly the same, but so in position Z1, we will add 0.8 ppm. This is what you did. And in position Z2 here, we should have the O-methyl group, and the O-methyl group has a de-shielding effect of 14.4 ppm. Is it what you have done?
And it is equal to 114.9.
Yeah. For carbon 3 now?
Uh, uh, plus 1.0, 1.5.
Sorry, you say?
Yes, I say then plus 1.5 and plus 1.
No, just let me check. So we have in position 2, we have this 1.5, yes, and in position 3, yes, that's it. Which is, what's the result?
131.
So did you understand, or we should do all the carbon? It's okay for all of you?
Yes.
Yeah? Okay. So with this kind of calculation, remember the exercise we did last time? We worked only on proton, but as you could see, we can do the same for carbon 13. So I have almost finished the lecture for the carbon 13. So that, and then when we have made this calculation for the theoretical value, then we can compare with the real spectrum. And we can, especially for the carbon that are close in chemical shift, we can choose and assign which one is which one compared to the theoretical value. So this is for aromatic ring could be very easy. Not very easy, but it could help a lot doing this calculation. Maybe we can also play a little bit with this. Remember, we talk about equivalence between protons. And when protons are equivalent, they have the same chemical shift because they have the same chemical environment. Of course, it's the same for the carbon 13. So if we have equivalence between carbons, that means that we have a symmetry in the molecule. So can you tell me for each structure how many different peaks, different signals I should see on a carbon 13 spectrum? For example, for the first molecule. First molecule. How many different chemical shifts that mean? Do you see a symmetry in this molecule?
Yes.
Is it a plan, an axis? So if you see a symmetry, can you tell me how many signals we should see on the spectrum?
There is a symmetry, so I think we should see two signal.
Only two signals?
Yes, I think.
For which carbon?
Mm, wait. No, I think there would be three.
For which one?
One carbon the further away from the branch, and the other two.
I'm not sure I understand what you have said. Can you repeat, please?
So if we consider the top carbon of the ring as the position 1, then
This one?
we in the yes that one. Then we have the signal of that one, the carbon next to it on the left, and the carbon on the furthest away at the above the ring.
You mean that one and that one?
Yes. Yes.
Okay. So you mean for each of them a signal?
Yes.
And what about that?
All the two carbon of the ring is the symmetry of the other one.
Okay, we have a plan of symmetry here. It's just like a mirror.
Yes.
Okay. So we should have a signal for the methyl, a signal for this carbon, a signal for that one, and a signal for this. So in total, 4 different signals. Okay, for everyone? Yes or no? These two are equivalent. They have the same chemical shift. These two are equivalent. They have the same chemical shift. And this one is alone, so it has its own chemical shift. And the methyl are equivalent, so they have the same chemical shift for both of them. Okay, for everyone?
Okay.
Or let's say signals. What about molecule 2?
And for molecule 2, there is no symmetry, so we should expect pi signal.
5 signal, but for these, for the ring,
Yes.
you forgot, every time you forgot the methyl. I should see the methyl.
The but the ship is okay.
Yeah, we have an axis. This, in the first molecule, we have a plan. Symmetry, I don't know how to draw that, but you have a plan of symmetry. Excuse me. In that one, you have an axis. The molecule can go around the axis, and then you can see that this methyl became that one, and that became this. So here, the two at the same thing as before, we have one signal for the two methyl. So one signal for these two. One signals for these two, and one signal for the last one. So again, we have 4 signals in the spectrum. Okay. What about the molecule 3?
Well, could we have the plan synergy across the triangle. So
Mm-hmm.
so we should expect also for signal.
For what?
One carbon which doesn't connect to any branch. One of the 2 carbon of the ring and 2 other carbon.
Sorry, that one.
Yes, and one of the 2 carbon in the ring.
Say here and here,
Yes,
and
2 carbon outside.
are they different?
Mm,
No, they are
I
not.
think 2 carbon connect to 1 carbon in the ring. They not different.
No, they are not different. Why?
Okay.
Because we have both an axis of symmetry and a plan of symmetry. I don't know how to draw that, but we have a, sorry, we have a plan here. You understand what I mean?
Okay.
And we have also an axis of symmetry. So here we should have one signal for 4 carbons, another signal for 2 carbons, and another for 1 carbon. So here we have 3 different signals. And what about the last one?
If we consider the top carbon as a position 1, then we move to the carbon at position 3, and we have the plan synergy that go to the other side.
Mm-hmm. So,
So we should expect on for signal.
um, Do you agree with me that here you, for each position, you have 2 protons, right?
Yes.
Are they different one to another?
Hmm.
As I have CH2 all around. They are all the same. There is no heteroatom, no methyl, no substituent. So all of them has the same influence, let's say. So they will be all the same. So same chemical shift, only one signal. We are on carbon 13, okay? But in proton, it will be the same. I will have only one signal for all these protons. It would be different if here I had something like that, for example. Okay?
Okay.
So here are the solution for this exercise. So here we have a plan of symmetry. Here we have an axis. Here we have both. So 3 signal. And here the molecule is completely symmetric. So we have only one peak for all signals or all carbons. So it's almost the end of this lecture. So how can we interpret NMR spectra? It will depend on if we observe carbon or proton. Let's say for the most often observed. And of course, for the proton, we will have more information because we can use the integration and also the multiplicity. But for both of them, carbon and proton, if there is a symmetry in the structure, we should see it because we have equivalence between either proton or carbon 13. So 2 equivalent proton or carbon will have the same chemical shift. And in proton, I will see it easier because the integration will tell us that I have 2 or 3 protons at the same chemical shift. This is the first thing. Second, both for proton and carbon 13, the chemical shift will be very important to interpret what kind of molecule it is, but also what kind of chemical groups I have in the structure. Is it an aromatic molecule? Does it contain a double bond? Does it contain a carboxyl group and so on? So the value of the chemical shift will indicate what kind of molecule it is and what kind of chemical groups there are in the structure. Third element is the integration, as I said. So only proton will bring this information. So I can see properly if I have a symmetry in the structure or not. And fourth element, for both proton and carbon 13, I can use the coupling effect interaction and measure the coupling constant either between protons or between protons and carbon 13. And this will give us information about the sequence. That means the sequence, that means that the chain, we start by a CH3 and on the side I have a CH2 or a CH or nothing, depending on the coupling constant or the absence of coupling. And also, we didn't talk about that, but also we can see interaction with other elements, just like fluorine, phosphorine, nitrogen, of course, and the value of the coupling constant will be different of that we have for proton-proton or proton and carbon-13. So these are all the elements or information we have to learn to work with in order to determine the structure of molecules. This is just to conclude and show you that depending on the nucleus we observe, the most used for organic molecule. We talk about proton and carbon-13, but when you work on protein and peptide, we can, and also sugars, for example, the glucose phosphate can be observed, and we observe the phosphate, but not the carbon or the proton. Then you see that the natural abundance is different depending on the nuclei. Most abundant are hydrogen, fluorine, and phosphorine, I don't know. And the lowest is the nitrogen. So it will depend on the field B0 to have the best sensitivity if you want to work with this kind of nuclei. You see also that the range of observation is different for the chemical shift. We talk about proton and carbon-13, but you see that the frequency, the range of frequency of resonance is different depending on the nuclei we work with. And of course, the reference that should be used will be different depending on what nuclei you work with. So this is the end of my lecture. I will not go further to two-dimensional NMR spectroscopy. I think it's too difficult to teach in Visio like that, so I will stop there. And tomorrow I would like you to I will stop this. I have sent you some exercise. So for tomorrow, if you want, we can make the correction and work together to try to manipulate either proton and carbon-13 spectrums. Do you agree with me?
Okay.